Alright, so what we're going to do here is a very quick section. We're just going to look at some of the methods we use to solve systems of equations from 3.2, and we're going to do that with data. So we're going to revisit this problem from the first section in this chapter, the life expectancies of women and men. Were given by the system. So, if you recall from that section, when we did this, we just, we used our calculator. But now that we know substitution and elimination, we could potentially solve this system. We could solve this system by hand. So we're going to solve that system, and we're going to find when their life expectancies will be equal. So, and then we're going to interpret the result. So how do we do this? Well, so the first thing you want to do is, if you want to solve the system, you want to find when they're going to be equal. Well, that implies you're just going to set both of the models equal to each other. That's all you're going to do. So let's do that. So I have this. Equals this. Now that I have them equal, solve for t. It's as easy as that. So bring all the t's to one side and bring all the numbers to the other. So I'm going to bring the t's to the left side. So I'm going to subtract 0.208t from both sides. And I'm going to subtract 77.44 from both sides. Okay, so that's going to cancel. That's going to cancel. So now I'm left with, on the left-hand side, so I have decimal values of t. So pop out your calculator. So I have 0.115 minus 0.208. Hit enter, and I get negative 0.093. So it's negative 0.093 t. All right? And that's going to equal the right-hand side, which, when you do the math on that, right? So 69.86 minus 77.44. That equals negative 7.58. Now, to get t by itself, you're just going to divide both sides by the coefficient, which is negative 0.093. That cancels that out. So you're just left with t. So this divided by this. So negative 7.58 is already in there, so I'm just going to take that and divide it by negative 0.093. And I'm going to get 81.5 approximately. That number sounds familiar to me. So that's the t coordinate. But now how do I find the y coordinate? Well, I take that and I plug it into either w of t or m of t. So I'm going to take this and plug into w of t or m of t. It doesn't matter which one. I'll plug it into the woman life expectancy function. So w evaluated at 81.5. Just plug it in. 0.115 times 81.5 plus 77.44. So whip out your calculator. So 0.115 times 81.5 gives me that. And I'm going to add that to 77.44. And it's going to give me 86.8. So my solution set and this should look familiar to you already, is the order pair 81.5, comma 86.8. And that's the exact same thing we got when we did this in our calculator in section 3.1. So if you go to y equals, and I'll do it again just to show you for completion if you don't believe me. You plug in that system again into your equation, or in your calculator, 0.115x plus 77.44, 0.208x plus 69.86. Graph that. I might have to adjust the zoom, so let me zoom fit. Okay, let's adjust this. So just bear with me for a second. Zoom out. Getting closer. Let's move this over to the right a little bit more. Alright, now let's zoom out from there. We should get the intersection point in view. And we do. Okay, so now if you do second trace, go down to intersect. First curve, enter. Second curve, enter. And then guess, enter. There's the intersection point, which is exactly what 81.5, comma 86.8. And we got that in, we did that in 3.1. So, yeah, same answer. Duh. How do you interpret this? So, again, just for reference, T is the number of years since 1980. And the life expectancies, which is denoted by M, W of T and M of T. So this is in years, so this is the age, right? In years. So this right here is T, right? Comma, and this is the life expectancy, which is denoted by W, T, and M of T. So I'll just put W of T and M of T because they both represent the same thing there. They both represent the same thing. This is years, comma, age. So if this is the number of years since 1980, then, so let's say that's 81.5. So if we round that up to 82, right? So 82 plus 1980 gives us the year 2062. So in the year 2062, comma, the life expectancies of men and women are the same age of how many years? 86.8, so 87 years of age. Well, that sounds kind of redundant. I said age twice there. It's a little redundant, so that's good enough. Let me get rid of that part. Again, the interpretations are open-ended slightly, so that was a little redundant on my part, but again, this is good enough. So in the year 2062, the life expectancies of men and women are the same age of 87 years. Yeah, so we've already looked at this problem, so that was pretty familiar, but that's how you do it by hand. So on the back of these notes, there's only one-page notes for this section. We're going to look at it like a whole word problem here. So in this problem, what we're going to do is we're going to actually build two linear models, and then we're going to solve the model, and then we're going to interpret the result. Okay, so this is it's a lengthy problem. There's a lot to it, but it's really not bad. It's just there's a lot of steps. So what we're doing here is we're looking at a 2011 Acura RL and a 2011 Chevrolet Impala LS. And we want to know when these 2011 cars have the same value. Now, it says here, assume that the cars are brand new in the year 2012. Okay, so before we start anything, we need to define some variables, right? We need to define some parameters, I should say. We have to start variables. So this, little tip here is a good way of, starting us in the right direction. Assume that the cars are brand new in the year 2012. So what do I mean by that? That's saying, like, imagine t equals 0 is the year (2012). So I know technically they're 2011 cars, but if you think about it, 2011 cars, they are considered brand new in the year 2012. That's what we're assuming, that the cars are brand new in the year 2012. So t equals 0 is the year 2012. So what I'm saying here is we're treating 2012 as like the base year. That's the year that the cars are brand new, right? Based on our assumption. So we're going to let t, so based upon this, we're going to let t be the number of years since 2012. We're defining that. We're letting t be the number of years since 2012 because of this little tip right here. Okay. What else should we define? Well, we should define something for the value of the cars, right? So so we're looking at the value of an Acura and the value of a Chevrolet. So we should define a function that measures the value of the Acura RL. So I need to think of a function name for the Acura RL. Since Acura begins with the letter A, I'm going to use A of t. And the Chevrolet Impala, since that begins with a C, I'm going to use the letter C. So I'm going to let A of t and C of t I'm going to let A of t and C of t be the value of the Acura, RL, and Chevrolet Impala, respectively. Okay, so now that I have my variables defined, now I'm ready to make my system of equations. Okay, so I need to derive a system of equations that, measure the value of each car. So since we're dealing with linear equations, we need a function for A of t and a function for C of t, right? So we need something that looks like the following. A of t and C of t, these are linear equations. We haven't talked about any other kind of equation, so they must be linear. So they should take the form, we should know this by now, mx plus b. Right? Well, actually, technically, we shouldn't be using, actually should be using T, right? My bad. Right, because the independent variable is T here. Okay, so all we need to do is figure out the slope and the y-intercept for the Acura function, and the slope and y-intercept for the Chevrolet function. Once we do that, we will have a system of two equations. Okay. So, let's look at the slope first. So, if you remember about slope, right? The slope is a rate of change, right? Remember we talked about that in the past, in chapter 2? So, we need to find a value in our problem that talks about the rate of change of the value of each car. Is there any value in this problem that does that? Yes, there is. So if we look at the Acura, right? The Acura cost $37,120. Okay, well that's not a rate of change. But if we look down here, the RL, that's the Acura, so the Acura RL depreciates. Oh, there it is. Remember that gas tank problem? It was consuming gas. It was consuming gas per mile at the gas tank. So consuming implies negative. This is depreciates, which also implies negative. So depreciates by $4,245 per year for the Acura RL. And the Impala depreciates by $1,200 per year. So those two values right there are talking about some rate of change. So what's the rate of change? Dollars per year. Dollars per year. Something per something. So remember, slope is a rate of change. So these two values here are talking about the slope of the Acura RL and the Chevrolet Impala's value per year. They depreciate, right? Cars depreciate in value. How much? $4,245 per year and $1,200 per year, respectively. So we know what the slope is for each value of the car. So A of t is going to equal, so what's the slope of the Acura car? It's going to be $4,245 per year. And since it's depreciating, the value is going to be negative. So this is going to be negative 4,245 T plus B. And for the Chevrolet, that's also depreciating. So that's going to be negative 1,200 times T plus B. Okay. So we figured out those two values. Now I got to figure out the B values. We got to figure out remember, what does B represent? That's the y-intercept. We got to figure out these. So the y-intercept is it's the value of the function when t equals 0, right? So these are the A of t and C of t intercepts. That's the intercepts of each function, and that's the value of A of t and C of t when t equals 0. That's what the intercept means. This is what's these values when the t values when t variable is 0. So we have to interpret what this means. That's saying, what's the value of these cars when t equals 0? Well, what does t equals 0 represent? T equals 0 is the year 2012. We said that at the beginning. 2012 is when the cars are brand new. So the intercepts are the values of each car when the car was brand new. Intercepts are when each car was brand new. Okay, well, does our problem give us that? It does. A 2011 Acura RL cost $37,120. A Chevrolet Impala sedan cost $14,050. So those right there are the values of each car when they're brand new, which is the Y-intercepts. So now we know our models completely. So the Acura RL is negative 4245T. What's the car brand new? The Acura? 37,000. So that's going to be plus 37,120. And the Chevrolet function is going to be negative 1,200 T plus its brand new cost, which is 14,050. And that right there is our system. This is the value of the car of the Acura RL, and this is the value of the Chevrolet Impala T years after 2012. Okay, so now that we have the system, now we can answer the question. When will these 2011 cars have the same value? In other words, when will these two cars be, when will they be equal? When will they have the same value? Set AFT equal to CFT. So when you do that, it's very similar to the problem we just did. So you're going to have negative 4,245 T plus 37,120 equals negative 1,200 T plus 14,050. Now we just do the same thing we did in the previous problem. Bring all the T's to one side, bring the numbers to the other. I'm going to get T by itself, right? So I'm going to add 1,200 T to both sides. That gets rid of this, and then I'm going to subtract 37,120 from both sides. That gets rid of that. So the left-hand side becomes, so negative, here's my calculator. So negative 4,245 plus 1,200 is negative 3,045 T equals 14,050 minus 37,120. Whoa, I messed that up, didn't I? Here we go. Negative 37,120. Enter. Negative 23,070. Now finally, to get T, just divide both sides by negative 3,045. So you're going to get T equals, so that number divided by negative 3,045 is going to give us approximately 7.5. I'll say 7.5. I'll round to the hundreds place, so 7.58. So I'll put an approximation there, 7.58. Okay. So this is the number of years since 2012 when the cars will have the same value. But we want to find the actual value, their common value. So how do we figure that? To find their common value, we're going to plug this value into either the AFT or CFT function. So I'll pick the Acura function. So I'm going to plug in 7.58 into the Acura function. I'm going to get Negative 4,245 times 7.58 plus 37,120. And it's going to be an approximation, so let's go through that. So I'm going to have negative 4,245 times 7.58. That gives me that, and I'm going to add 37,120, and that's going to give me roughly 4,942.9. Now, let's say I plugged this into C of T, just for argument. Let's say I did that. So, if I plug this into here, let me just show that. Like, what if I chose to plug it into the Chevrolet function? So if I go through that, so negative 1,200 times 7.58 plus 14,050 gives me 4,954. So if you look at these values, you know, they're not exactly the same. You know, this one's 4,942, or, you know, if I rounded this up to 43, this is 54. There's a difference there of about, like, you know, 11, right? There's like an 11 there's like 11 difference there. But you have to keep in mind, you know, since we're approximating, you know, you're going to get some error there. But, you know, when you're buying a vehicle, the difference of $11 is pretty negligible, so we really don't care. Yeah, it's like, you know, what's 11 bucks when you're buying a car? So either one of these will work just fine. So our solution is the ordered pair 7.58 comma, and you could pick either one of these. I'll pick this one, 4,954. Now, that's a 5. I know my 5s look horrible. So how do we interpret this? That's the last thing we need to do. So, again, this represents the number of years since 2012. So if I rounded this to the nearest whole year, which would be 8. So 8 years since 2012 is this year, 2020. So in the year 2020, the cars have a equal value of, and I'll say approximately, $4,954. So, you know, that's the basic idea. Now, you know, if you use this one or this one to interpret the result, that's okay. You're going to have some changes, especially if you use the approximated value. If you plugged in the value you got when you actually solved the system, you would get the same values, because you would get, you know, you're using the exact value as opposed to the approximated value. So, yeah. So when it comes to making these equations, you know, this problem, you know, there's a lot to it. You had to define the variables, you had to set up the system, and then you had to solve the system. And then once you did, you had to interpret the result. So, you know, these are the kinds of problems you could see in this section on your homework, and you know, they're pretty straightforward. If you want to find a common point, you just want to set the models equal to each other. Yeah. So yeah, that's all there is for this section. It's a pretty relatively short section. So in the next section, 3.4, we're going to look at word problems, which is everybody's favorite section. We're actually going to look at, you know, how you can make a system of equations or even a single equation from an actual word problem, and then solve the word problem. So yeah, so that will be 3.4, and so all right, that's the end of this video.